Hi, welcome back. Now, in the previous session, we had explored some options like correlation, covariance, sampling, rank, and percentile. In this session, we'll discuss some of the tests which are available in Excel, and then we'll also discuss regression. Now, the first test which we'll discuss is ANOVA, and it stands for Analysis of Variance. Now, let's say I've got a class which has 30 students, and they've been divided in three groups of 10 each. Each of the groups is assigned a different math teacher, and then the exam results are assessed to see if the students get the same marks irrespective which teacher taught them. So this is my group A marks, this is my group B marks, and this is my group C marks. And the null hypothesis is that the means across these groups is same. Now the odd thing is that this is ANOVA, which stands for Analysis of Variance, and our null hypothesis is based on means. But why it is called ANOVA is because we are analyzing variance over here, and thus we will be inferring about the mean or the population. So let's see how this works. I'll go to data analysis. I'll click on ANOVA single factor. So this is our data over here. Labels in first row, and let's have the level of significance at 5%, which is 0.05, and I'll have the output in a new worksheet. Click on OK. So this is how my output will look like. Let me just format it a bit. Now for each group, I've got the number of observations, I've got the total number of marks, basically the sum, I've got the average number of marks, and I've got the variance also. Now the second table is the ANOVA table. Uh, this is the source of variation between groups. So this is the sum of squares for between groups. This is the sum of squares for within groups. This is my degrees of freedom. So in total, I had 30 observations, and now I'm left with 29 degrees of freedom. So in very layman terms, just to think of how degrees of freedom works is, let's say you've got 10 numbers, and you want that the sum of these 10 numbers needs to be equal to 100. Now for the first 9 numbers, you can select any number you want. You can select 10 or say 11 or 15 or whatever. But for the last 10th number, you would have to ensure that the number needs to be such that the sum for all these 10 numbers is equal to 100. So that is why for 9 numbers, you've got freedom. So this is a very layman explanation of degrees of freedom. Then you've got mean sum of squares over here. So basically this is calculated by sum of squares divided by the degrees of freedom. Then you've got the calculated f over here, which is this divided by this. And this is the p-value, and this is the f critical or f tabulated value at 5% level of significance. Now in order to test the hypothesis whether this is significant or not, we will compare these two values. So since f calculated, that is 2.422, is less than f tabulated or f critical 3.54, we cannot reject the null hypothesis that all the marks are equal. We can also compare the p-value with the level of significance. Since this is greater than 0.05, which is our level of significance, we cannot reject the null hypothesis. F-test. Now an F-test is used to compare two population variances. The null hypothesis is that the variances of the two populations is same, and the alternative hypothesis that the variants are not same. Let's assume we've got 20 students in a class who are divided in two groups based on their gender, and we need to see if the study hours are different for both the groups or not. So over here I've got the study hours for both the groups. So let's go to data analysis, F-test. Variable 1 would be this, variable 2 labels. Let's have this at 5% level of significance. Click on OK. So mean is a descriptive statistic, same as variance. So these are my descriptive statistics over here. Then I've got 10 observations. Degrees of freedom is 9. Now my F calculated over here is 0.7948, whereas my F critical is 0.31457. Now this F is calculated by dividing 6.888 by 8.667. Since this F calculated is more than F tabulated or F critical, we reject the null hypothesis that there is no difference between the study hours of the male and the female population. Let's move on to the third test, which is the Z test. Now this test is used to compare means of two sets of data to see if there's a difference. So our null hypothesis is that the means are same, whereas our alternate hypothesis that the means are not same. And now we've got marks of 24 students before and after taking maths coaching classes. Now let's see if there's a difference between the mean of the two populations. So what we'll do, we'll go to data analysis, and we'll use a Z test. Now, one of the prerequisites for this particular test is that you need to calculate the variance also. So let me just cancel this. So I've calculated the variance for both these samples using the formula var.s. So this will give the variance of the two populations. Let's go back. Variable one range, variable two range. Let's say that the mean difference is 0. Let's calculate at 5% level of significance and the output at new worksheet. Click on OK. Now over here I've got the mean, I've got the variance, I've got the number of observations. We were testing for the difference between the mean of the two populations as 0, or basically saying that the mean of the two populations is same. Now using the p-value over here, we can compare it with the level of significance alpha, which is 0.05. Since this value is greater than 0.05, we cannot reject null hypothesis and we accept that the mean of the two populations is same. Now t-test is used to test the null hypothesis that the means of the two populations are same. This test is used when the number of observations in our samples is usually less than 30. For greater than 30, we usually prefer the z-test, which we've just discussed. Now there are three types of t-tests in Excel. The first one is paired to sample for means. That is when the population or sample on which the test is being done is same. For example, marks obtained by a group of 10 students before maths coaching class and after taking maths coaching class. That is, the sample population is the same 10 students, just that their performance is being compared before and after an event. Then we've got two sample assuming equal variance. That is when the samples are different, independent of each other. Let's say, for example, two groups of 10 students being compared with Excel, assuming equal variance. The third one is two samples assuming unequal variances, just similar to two sample assuming equal variance, just that over here the variance is either unknown or different. Now the null hypothesis can be that the mean of the two samples is same, in which case it is a two-tailed test. For a one-tailed test, null hypothesis can be mean of population A is greater than mean of population B or vice versa, with the alternate hypothesis being that the means are different. So we'll over here test that the means are same and the alternate hypothesis that the means are not same. So for a paired two sample test, We'll go to data, click on data analysis, click on OK. Let's put this to 0. Pulse. Now comparing T statistics this with T critical, T statistics is greater and hence we reject null hypothesis and conclude that the difference between weight before and after is not due to chance. Let's look at the second t-test with unequal variances or where the variances are not known. So we've got 24 students over here, their marks with tuition and marks without tuition. And these students are independent of each other, so they are not the same students. Let's put this to 0 again. Click on OK. Since T stat is less than T critical, we do not reject the null hypothesis and conclude that the means of the two populations is same. Now let's move on to the last part of the video, which is regression. Now regression is used when we want to estimate the relationship between two or more variables, a dependent variable and independent variables. In simple terms, the independent variables will form an equation which helps in estimating the value of the dependent variable. Over here, the salaries are dependent variable, and we've got two independent variables. One is successful projects and age. So let's say we want to estimate salary on the basis of these two variables. So we'll go to data, we'll go to data analysis, regression, click on OK. Input y range is this, input x range is this, labels, confidence level is 95%, which is fine, and then we'll click on OK. Now in the first table, regression statistics, we've got r square as 0.925, which implies that the model or the equation which we have created over here using the two variables, successful projects and age, that particular equation can explain 92.5% of variation in the dependent variable. The maximum value of r square is 1. So the closer our r square to 1, the better our equation. Now, how to identify the equation over here? So we've got this as our constant plus into successful projects plus into age. So this is our equation. So this is an intercept term over here. This is always going to be constant. Then for each and every successful project, we'll multiply it by 903.04738822. Basically, this is a coefficient for successful projects, and for age, we've got the coefficient as 891.88. Now to see if both these independent variables are statistically significant or not, we look at their p-values, and these p-values should be less than 0.05. Over here, if you look at the p-values, they are very less as compared to 0.05. Hence, all three of these variables are statistically significant. If one of these variables is not statistically significant, then we need to delete that variable and start with the entire model building or equation building again. Now, having discussed regression, we are now through most of the options in data analysis. If got any questions, let us know. Thank you.